This is the Chapter 13, Part 1 video podcast for field methods in hydrology on the topic of water quality. Now, so far in this course, I've really tried to emphasize the water balance. And although each lecture has not been coming back to that big theme, it's always been there. We've been looking at the variables that relate to different aspects of the water balance. And we will continue to do that throughout the quarter. But it's important to remember that big picture because the first thing you always want to think about when you're getting going with field work is the structure of the water balance that you're going to be monitoring. In addition to that basic water balance of how much water there is in storage and flux in different areas, there's also the question of what is that water carrying. Now, water carries energy, and so we often have an energy balance, especially if you're dealing with evapotranspiration. But there are other things that it carries, which could be sediment, nutrients, metals, and other organic matter, a variety of constituents. And indeed, you can have you can have a mass balance for any and all of these other constituents. So we can address the topic of water quality in a similar fashion, in a very hydrological fashion that emphasizes mass balances of how things are moving. And thus a field methods approach would be in order to characterize those abundances in relation to water abundances. However, there's more to the topic of water quality than just these fluxes. There's a lot to do with the effects of pollution, both to nature and to people. And there's a whole lot of policy infrastructure related to that. So it's worthwhile to use this Part 1 video podcast to just think about some of these background issues. Just as a motivating factor, there are two photos on the right of a lake that's in Indonesia. And as you can see, although it's translucent, it's bright blue. And I actually received an email once with a question with these photos saying, hey, we've got a TV personality who's out having an adventure and they've come across this lake and they'd like to know if they can drink this water. After all, it's not like turbid per se, but should we be worried that it's bright blue? And so, I did a little bit of research on it and was able to answer that question. And if you would like to have a little extra credit activity, you can go ahead and take these photos. I can tell you it's Indonesia, and you could try to figure out whether you think it's safe to drink the water, write up a little one-page summary of what you did to look into that and turn that into me, and I can assign you some extra credit for doing that exercise. So water quality is defined as the physicochemical state of water used to assess suitability for ecosystem health and for use in municipal, industrial, and agricultural applications. And we are typically interested in worrying about the toxicity. What's the harm that can happen to people as a result of constituents? And how might that, what we call, bioaccumulate? And I'll come back to that topic. So with this video podcast, I want to talk about point and non-point source pollution and other basic definitions like bioaccumulation, biomagnification. I want to introduce you to some basic federal and state policies, and then I want to show you a fairly extensive case that I was involved with the sediment TMDL, which I'll explain what a TMDL is as well. In the Part 2 video podcast, we'll get into the field methods. There are a lot of common water quality problems in California, and I can't remember what document I pulled these out of, so I apologize for that, but it shows for rivers, lakes, coastal waters, and groundwaters that there can be significantly different constituents, things in water that people are worried about. For rivers, we think of it in terms of point and non-point source pollutions. I'll talk about that. But a lot of that has to do with nutrients and fecal matter, for example. Whereas in contrast with lakes, it could be sedimentation, metals and nutrients, of course. And with coastal waters, we have pesticides, trace elements. So you can look at this and just, I'll leave that for you to read, but there are typical water quality problems. There's some similarities across these water bodies and some differences. Point source pollution is any single identifiable source of pollution from which pollutants are discharged, such as a pipe. Now, in the limit, we could argue that just about anything is a point source pollution, but typically we think of a point source pollution as something where that pipe is not inconsequentially small, but is large enough that the EPA could say, this discharge, you need to be regulated and let's talk and work it out. In contrast, non-point source pollution involves many small sources of indirect or scattered pollution that enter a water system. This could be, all of us in our homes having nutrients that we use for our lawns or potted plants. It could be animals across the landscape, could be car emissions, a whole variety of things that are happening, and then all that together accumulate and have an effect. And so from an agricultural setting, a common thing here in California is the cow. So with a cow might consume 48 pounds of dry matter a day, of which there's 1.4 pounds of nitrogen and 0.2 pounds of phosphorus. Then they release 0.8 pounds of nitrogen and 0.12 pounds of phosphorus. Well, that's 2/3 or so of the nitrogen and about half of the phosphorus. So it's just passing right through. I mean, you might as well just be dumping these compounds right on the ground, but they're just sort of passing through the cow. So it is a substantial amount of nutrients. In some cases, it might have been there anyway. If it's just naturally produced from nitrogen fixers, that then the cow is taking advantage of, but not always. And it may be that they're concentrating it and making it available to the water system in a way that wouldn't have happened without the cow. And I don't want to put all the blame specifically on cows, of course, but just an example. Now, when we have some kinds of compounds, especially toxic metals, but also some organic compounds, they have the ability to bioaccumulate and biomagnify. Bioaccumulate means that if you're one individual and you're consuming the toxic material, that your body preferentially sequesters it or holds onto it. It could be that it's stored in fatty tissue, could be in muscle tissue, could be in bones. There's different possibilities there, but whereas other kinds of things are cycling through, like that example of nitrogen and phosphorus in a cow where most of it is leaving, a lot of these toxic pollutants are not needed by your body in any beneficial way, or they are needed but in much smaller concentrations than are being stored up. So that's bioaccumulation in an individual organism. Biomagnification occurs when individuals are accumulating or bioaccumulating toxic pollution, and then something higher on the food chain eats those individuals and is taking in even more. So, if one organism has a concentration of 5 milligrams per liter, but then the next level up you see 30 milligrams per liter or 100 milligrams per liter, then that would be a biomagnification. And the classic example of a human-caused disaster for this is the mercury that was consumed by the people of Minamata, Japan in the 1950s. And this was an industrial source of mercury that was first ingested by fish and shellfish, which were then in turn consumed by the citizens who ate that as their primary food source. And in 1956, there was an epidemic with a whole host of human health problems, but including many people dying and suffering other major problems. It's still difficult to know how many people were impacted by that, but it's estimated that it was around 10,000 people. And this isn't the only example. There are plenty of other cases, especially with mercury associated with its use in gold mining around the world, where there are cases where large amounts of mercury can be measured, say in mother's milk that's being consumed by babies, because the mothers have bioaccumulated and large amounts of mercury. So that leads us to toxicology, which is the study of the effects of chemicals on organisms, trying to figure out whether we're going to have either acute effects, acute mean like leading to death, or major problems in the short term, or whether there would be chronic problems that could take a long time to emerge and might emerge at a lower level. One of the metrics that's commonly used in toxicology is called an LD50, or lethal dose 50. This is the concentration of a chemical that kills off half of the population that it's applied to. So that's a pretty extreme number, and of course we don't want to be exposed to chemicals at that concentration. But we often don't want to be exposed to chemicals at far, far lower than just that concentration, because we could have chronic effects. And I know that this graphic is pretty hard to read. You can find something like this on the internet, but one of the ones that's been in the public eye quite a bit is TCE, trichloroethylene. It's an industrial compound that's used, and it has a lot of difficult effects, but there are many others that people are exposed to. This is just one example. So from a policy perspective, a lot really got underway with the 1972 Clean Water Act. It's the cornerstone of surface water protection for the United States. Note that it doesn't directly deal with groundwater or water quantity issues, so it's a water quality thing. And here's the four things that it does primarily. It develops water quality standards. Then water bodies are monitored to determine if the water quality standards are being met. If they are being met, then it tries to set up a program to ensure that the standards are adhered to into the future. If it's not being met, then a strategy has to be developed to try to get up to those water quality standards. And the most common type of strategy we see today is a total maximum daily load, or TMDL approach. It's just what it says. The only word here you might not be familiar with is load. Load would be like kilograms per day of a constituent. Hopefully not kilograms, hopefully more like milligrams or micrograms. But so it's the total amount that could be moving down the river, past a gauging station or something like that. It's the total amount that would be passing through that system on any given day. Okay. There are a variety of tools that the Clean Water Act uses to help to get there. The first is this National Pollutant Discharge Elimination System that addresses point sources. Section 319 that looks at voluntary programs, what we call BMPs, or Best Management Practices. Section 404, which relates to dredge and fill materials. So even if you're removing material, the fact that as you're removing it, you're going to be causing turbidity and stuff could be spilling off the shovel, so to speak, then Section 404 deals with that. Section 401 is certification of approval from a state level agency, and then the state revolving fund that provides large loans for pollution management. Here in California, we have what's called the State Water Quality Control Boards. This was created by the state legislature in 1967. It's a 5-member board that sets statewide policy, and then it supports what are called the Regional Water Quality Control Boards. It's also responsible for allocating surface water rights, and there are 4 programs for water quality, financial assistance, water rights, and enforcement. The Regional Water Quality Control Boards are really where a lot of things get done, and I've shown a map of California in those regions. And one of the things you can notice right away is that the Central Valley board is really quite large, and this is on a watershed basis, so that governs these delineations. So there are 9 regional water quality boards. They're semi-autonomous, and they set the requirements related to each particular watershed. But then they also are responsible for determining compliance and then ultimately possibly even enforcing the standards that are there. And it's incredibly challenging because you have to figure out, well, what's the baseline natural condition, and then what are the effects of individual land uses? How do you account for historical things that aren't caused by anyone today? Who do you blame? How do you address that? So there's a lot of challenges. And then, of course, California has a lot of natural variability to it that confounds things like wildfires and other disturbances, droughts and floods. So let me show you an example of one TMDL that I had some involvement with. Now I'm going to show you the materials that were publicly available, so there's nothing secret here as I broadcast this across the internet. But this is what was available when I got involved in about 2003, 2004, and tried to help with some of the science related to suspended sediment draining to the Salton Sea. And the basic question that's here is, how much suspended sediment should be permitted to move through agricultural drain channels and rivers in a region? And what are the biggest contributors of suspended sediment? So the Salton Sea drainage system, the Salton Sea itself, as you can see in this photo, is a large body of water in an inland watershed. It drains to this depression. It doesn't drain to the ocean. And it wasn't historically present, but as a result of irrigation water, then now there is this large area that's really shallow and heavily impacted by a lot of chemicals and sediment that come as a result of that. I mean, you can see the ambient terrain and the irrigated terrain and how dramatically different those are. On the right here is a map that shows the drain network. The Salton Sea is in the upper left, not shown. And then there are these two blue lines, which are the New River on the left and the Alamo River on the right. And they look pretty much like typical meandering, lowland rivers. Off of those is an extremely high density drain network that is composed of irrigation ditches. They are both water supply canals and drain channels, and this is the drain network. And there are some larger drains and then tributary drains to those. So groundwater is pumped up, and also Colorado River water is brought in, and that is the source of irrigation. Now, this is an area that would normally have very low flow in the rivers. So we have what I would call an irrigation-dominated watershed as opposed to a precipitation-dominated watershed. And the primary method of applying water is not particularly efficient. It involves sprinklers and furrows, and then that water drains to the main drains, which then empty into the rivers. I'm not sure. Oh, I see. Okay. Well, I don't know why. Sorry about that. Oh, that's too bad. Okay. Well, so this is a picture that shows furrow irrigation. So with furrow irrigation, you're basically flooding a field and having water go through the furrows. But as part of that, as you can see in the photo, there's a lot of sediment that gets picked up and carried down the drain channels. And then if you look at a drain channel like is shown here, this is one that has been recently dredged, but you could see it's dramatically oversized. I mean, it's, remember the topic of where's the floodplain? Well, believe me, there's no floodplain here. This is a terrace level, and then this is a deeply incised channel because it's been overly dredged. And so as a result of that excessive cross-sectional area, there's insufficient sediment transport capacity, and so the drain channels fill up with sediment. And then that requires periodic dredging to maintain the size of those channels. An alternative approach is to develop what are called regime channels, which are just sized and shaped and sloped to carry the material that's moving through them. But even with that, the fact is that you have this accelerated load of sediment as a result of the way water is applied to the land. What are some of the beneficial uses in a river like the New River? Well, warm freshwater habitat would be meaningful, wildlife habitat, preservation of rare, threatened, endangered species, the possibility for water contact recreation or non-contact recreation, and then finally the potential for industrial service supply, which doesn't depend on a lot of high quality water, but it could also be impacted as well. So these are the main motivators for why we want to have good water quality in a river like this. So now we have to figure out whether the conditions are harmed as a result of the water quality from that sediment. And this is where it begins to get pretty dicey. So if we turn to the impairment side, now we're in the realm of like, does smoking cause cancer and things like that. And so when we look at sediment, there's a scarcity of studies that look at what is the role of sediment in causing death or sublethal conditions and real harm to warm water fishes. Warm water streams are often muddy. It's not generally, the Mississippi River, the Amazon River, it's not like rivers can't have sediment in them and have to be sparkling clear. However, there are some standards here to protect aquatic life. High level of protection, 25 milligrams per liter. Moderate protection, 80 milligrams per liter. And then, low level of protection, 400 milligrams per liter. Now, here's what's really interesting is if we look at how these standards work, the National Academy of Science recommendations were based on literature surveys of the direct effects of suspended sediment on freshwater fish life cycles. And those were done by the European Inland Fisheries Advisory Council, which conducts studies on worldwide topics. This literature survey revealed that healthy fish sometimes occur at lower concentrations of 80 to 400 milligrams per liter total suspended solids. I'm sorry it's dark here, but death rate is substantially greater for fish for long periods in waters containing TSS in excess of 200 milligrams per liter than for fish in cleaner water. And only poor fisheries have values greater than 400. But the main thing here is that, here we have a European Inland Fisheries Advisory Council, which is, bringing a European perspective, which is being applied across the United States, including in this, super arid, hot region with an irrigation-dominated source of water. So it's, we're talking about a very uncertain chain of logic about what harms are from distant lands and long ago that isn't really particularly useful. And this is from 1964. So you can see that the link between physical processes, chemical contamination, and toxicological effects still requires a lot more research and thought. Here's going a step further beyond sediment and looking at a chemical compound like DDE. So Imperial Valley soil samples contain DDE of 21 to 343 parts per billion. The new river bottom sediment samples from 1990 were 7.4 to 11. The Imperial Irrigation District had samples that were from below what they could detect at 0.05 parts per billion to 111 parts per billion and averaged 48. So that's 0.05 to 111 or 343. But look at this. DDE chronic concentration in waters where people consume fish or other natural organisms should be less than 0.00059 parts per billion to protect human health, according to a 1999 EPA standard. Well, my God, and I noticed I marked it, is this right? But yeah, so you've got a standard here with 6 times 10 to the minus 4, and you've got values here that are orders of magnitude higher than that, which basically says it's just flat out hopeless to try to get back down to a safe level in those sediments. Okay, all right, so this is now the most interesting part. So in light of this, a proposal is made here that says that the existing total suspended sediment at this one site, based on the mean concentration of available data, so this is just all the individual samples whenever they were taken, like treating them all as if they were independent and identically distributed, suggests that it was at that time 306 milligrams per liter, and a proposal is made of a 35% reduction to get to 200. Why 200? Well, there's no particular reason stated for 200. It doesn't represent high, moderate, or low levels of protection. It's just basically, what do we think can be achieved? I mean, it's extremely difficult to do reductions in any case, but it's important to understand that regardless of the science is saying you need far lower values than, say, 80, but that, and then of course need to get DDE to these ridiculously low levels. But basically, this is just sort of like a level that feels good and is economically or politically feasible. So how are we going to do that? Well, now we turn to what hydrologists do, which is budgets. And in this case, we need a sediment budget. Sediment budget works the same as a water budget. What's coming in, what's going out, what's the change in storage. So here we look at the load. These are now loads, so like kilograms per day or something like that. The load that's in the drain equals all the different sources that are combined together. So what's coming from farmlands, what's coming from drain dredging, and so dredging could be a loss, but to the extent that dredging is releasing material that's otherwise locked on the bank or in the bed, then that's a source. In-stream drain erosion, wind deposition, stormwater runoff, urban runoff, and then from regulated facilities. So we basically set up a sediment balance here, and then you have to go and figure all of that out. So this just gives you an example of trying to take a policy, translate from the idea of what we'd like to achieve in terms of human health and ecosystem health into practical numbers, and then how are we going to go about tracking those, the changes to see if we're getting to our goal? And the answer is with a sediment budget. So I'm going to stop here. That's the end of part one. Just gives you some sort of background, and then we'll turn to the field methods themselves next.